Good morning. This is our third lecture of our course Vehicle Dynamics. In Module 1, we are going to revisit or learn fundamentals of mechanical vibrations, the basics. So we were doing that in the last class, understanding simple harmonic motion, because simple harmonic motion is an example of mechanical vibration, which is regular in motion. When you say vibration of systems, it is not necessarily a regular motion like a simple harmonic motion. It can also be irregular motion, like you observe the vibration during earthquake, the building vibration and so on. So those excitation is not periodic, and they are random, and those are irregular in nature. So that's not necessarily to be like a simple harmonic motion, but all are in the purview of mechanical vibration. So we were looking at a simplest case of mechanical vibration, what is called simple harmonic motion. So in today's class, we are going to look at again further the same simple harmonic motion. How can we put it in a more convenient form to look at the motion phenomena, understanding its motion, as well as understanding its response most clearly. So for that purpose, let us just look at what we were doing in the last class and then continue with the today's class. I will share my Active Inspire board. So hope you are able to see the screen here. So this is what exactly we were doing in the last class. We have seen simple harmonic motion with the help of the spring mass system, where you are describing mass of M is attached to a spring of stiffness K. And you could see here it is its free length. When mass is attached, then it is going to its static equilibrium position. At that time, it is balanced by mg is equal to k delta st. And then further from static equilibrium position, then you give initial condition for this. So the initial condition of two kinds. One is from this static equilibrium position, you can give an initial velocity. That means just to give an impulse from there. The velocity, because of that, the mass would be going to its extreme position, and where the velocity is zero, that's called point of reversal. Then it will be reciprocating about its stable equilibrium position. That is one way you can execute this simple harmonic motion. Or the other way is that you just pull this mass to its extreme position, and just from there you leave it. When you leave it, its initial velocity is zero, but its displacement is its maximum displacement. And then again it is going to undergo the motion. So either of this way you can initiate the simple harmonic motion on this mass M. You can also do in the other way, not necessarily with the two condition I said, in a general case. So you can have this is not to be pulled to its extreme XM in between somewhere like this at a position X from here. And that would be your initial observation time. So when it is displaced position, again you give an impulsive force, then it will be given a displacement as well as an initial velocity, and then also you can make this motion executed. And the governing equation of this motion can be obtained by applying Newton's second law. That's what exactly we were doing it in this class, and you see that we have got this equation 2 gives the governing equation. So the solution of this governing equation can be looked at by means of a trial solution. That's all what we were discussing in the class. So here is where there is some difficulty that we had. Case 1, case 2, all I will give a clarity today and then start our class. Right, and then you see we were also writing in a compact form. Instead of having x is equal to c1 sin omega nt plus c2 cos omega nt, you can also write it in this form of equation 10, 11, 12. So we will continue from here, and also we will understand the advantage of representation of this motion in a complex plane, in real and imaginary plane. So that's what is my objective of today's particular class, and we'll go ahead with that. So let me start stating that clarity of what was we were doing it in the last class once again. This is lecture number 3 on today's date 06/08/2021, and look at this spring with the mass attached, and it is in its static equilibrium position. Static equilibrium position. When mass is not attached, the free length will be somewhere here, and that is now moved to delta St, then it is its static equilibrium position. So this is stiffness of spring K. And I can now make this mass to undergo an oscillatory motion with reference to this static equilibrium position or stable equilibrium position, you can call that. So at t equals 0, now if I hammer this, if I give an impulse, impulsive force with small hammer, then what would happen? Here there will be velocity given, but this is that my reference where I consider x starts from here. So this is x naught, that's equal to 0 at this point, right? So if that is so, what was that our general equation that we have seen is yesterday, that is x is equal to C1 cos omega nt plus C2 sin omega nt, right? And then is it sine and cos or other way we have written? We have written other way around. So let me take it in the same form. C1 sin omega nt plus C2 cos omega nt. So x dot is C1 omega n cos omega nt minus C2 omega n sin omega nt, and x double dot would be C1 omega n squared minus sin omega nt minus C2 omega n squared cos omega nt. So this is what we have seen. So when you consider this is case 1, that you can always make your simple harmonic motion starting from its static equilibrium position. What is that? It's going to be there at t is equal to 0, you have x is equal to 0, and you will have an initial velocity, and that initial velocity x dot is going to be Vm, maximum velocity at its main position, because once you give an impulsive force, it will gain its maximum velocity, and then it is going to reduce in velocity till it's going to reach its maximum displacement. So at this position, it is this case. So if this is so, I can find this constant C1 and C2 with these initial conditions. So what is that? I'll have, if I substitute x is equal to 0 in this equation, and I'll have at t is equal to 0, C2 is equal to 0. So C2 is equal to 0. And in the second equation, if I put Vm and t is equal to 0, I'll have C1 equals Vm by omega n. Right? So this is one case. I can have its simple harmonic motion like this. Or the other case, case 2, is I have to give an initial condition taking this mass to its extreme maximum amplitude. So this is mass m, and this position from its mean position is at a distance xm. So I consider this is to be at time 0 observation. So I just have pulled this and I'm holding it. I'm just releasing it. What will happen when it is stretched? There is an energy stored in the spring, and when you release it, it's going to start from rest condition, and it's going to gain its maximum speed at mean position, and then again the speed would be decreasing and become 0 when it reaches the other end where it is minus xm, right? So this is what is that motion. So if you see at t is equal to 0 now, from first equation, what is my thing? I have t is equal to 0, my x naught is going to be xm. So substitute that here in first equation. So this is equation 1, 2, 3. In first equation, if I put this, it is going to be xm is equal to C2. So C2 is going to be, in this case, is xm. And what is my thing at t is equal to 0, V naught is 0. So in second equation, if I substitute that, I'll have C1 is equal to 0. C1 equals 0. So I can also have the second case to start its simple harmonic motion. What was that we were discussing yesterday is a general case to get a compact form. So what is that in general case that we see is case 3 is what is general case. And we have not stretched the spring to its maximum amplitude. Also the mass is not kept at its static equilibrium position. So the mass from the same static equilibrium point, it is not gone to this extreme position. Instead, it is at an arbitrary distance or in the distance x now at time t equals 0. So how can I do that? I can pull it to some distance and I can also give an initial velocity. If I do that, so I would also be able to execute my simple harmonic motion. So here what is the condition? At t is equal to 0, I have x is equal to some x naught. So this is at x. So that's going to be x naught, not xm. And I will also have v equals v naught. So now if I substitute that in equation 1 and 2, I will have now C1 is going to be v naught by m, and sorry, not m, omega n, and C2 is going to be x naught. C2 is going to be x naught. So these are all the three cases that one can understand. How can you initiate the motion of this particle mass m and make that to oscillate about its static equilibrium position to realize or to observe the simple harmonic motion. So the solution of the simple harmonic motion is given by equation number 1. And in that I have this initial conditions, I have this two constants C1 and C2. Their values can be determined with an appropriate initial condition. So the initial condition can be like in the case of case 1, case 2 or case 3. So this is what is that you should have in mind and clear always. So let's now look at, we were also representing the same by C1 vector and C2 vector. So that's what we were seeing in the last class. Is this. So you see here in the last class, what was that we were doing is this plot we have seen, right? So here you see that I have an auxiliary circle with a vector OQ having radius as maximum amplitude xm. In that circle, the motion of this point end of this vector OQ with a uniform velocity can represent the simple harmonic motion when this Q is projected on this vertical diameter. So OP vector is what is my vector x, and that solution what we had can be visualized here. So that is what is there we were doing it in the last class, and I just have to put you this diagram for a clarity. And you see here now OQ is my vector of consideration, and that is can be represented as resultant of these two vectors C1 and C2 vector. So here C1 vector magnitude and C2 vector magnitude is what we were talking of, those two arbitrary constants C1 and C2. And you see here the C1 vector is at a distance omega nt, and then from C1 vector you have this OQ vector at a distance q. It's at an angular position q, sorry, phi. So this phi angle is what is called the phase angle. Now we will understand that. And see now, if I project this OQ onto this diameter, this OP vector is what is my x vector, and that is what is now given its variation of this linear displacement from static equilibrium position, that's point O, is what is represented by this variation of amplitude as function of angle, or here this time I can put, or angle I can put. So if I put here, this is angle, it is omega t. if it is omega nt here, right? So omega nt if I take, and this is what is the period. The tau here represent a period. So this period is going to be representing one cycle, that's 2 pi, and that's what is equal to omega nt. So I can rewrite this here as omega Tp as Tp period as 2 pi by omega n. So here units in the numerator is radians, denominator is radians per second. So you know what is this omega n? It's called the circular natural frequency. So the word natural is because of free vibration. Why it is called a free vibration? We have seen 3 cases. That means you can either start the motion by giving some initial velocity at its equilibrium position and have the motion. Afterwards, you are not having any force on it. And we assume that system is independent of any resistances. So it's conservative system when you consider, and that initiated motion would continue forever, and that is going to vibrate or oscillate freely, so it's free vibration. So it's called a natural circular frequency. In that frequency, it will be vibrating, right? So you define here also a time period to complete one cycle from here to here. It completes one cycle. So here, how this is there is as you see, this is t. This is t. So here, what is taken is not omega and t. This t only. So if that is so, I will have here. This time period from one cycle to other cycle accordingly here, right? So instead of writing radians here, I will write now seconds. So how do I get this? 2 pi by omega n, I will put it. So 0 by omega n, 0 point, and then pi by 2 by omega n, then pi by omega n, 3 pi by 2 omega n, and then 2 pi by omega n completes one cycle. So what would be the time here? It is 0, and here it is pi by 2 omega n, and here it is pi by omega n, here it is 3 pi by 2 omega n, and here it is 2 pi, sorry, here it is 2 pi by omega n. So if this is my starting point just on this I mark. See, that's why here it is not from 0 or something, nothing is not mentioned, it's t scale. So if I consider one cycle like that, so if I mean here it's 0 and this is my starting point, what is that? It is similar to case 2, that I have my extreme the initial condition to be with the 0 initial velocity with the maximum amplitude. If I give and stop, and then it goes like this. So that is that cycle that I look at here, corresponding to case 2 I discussed just now, and is what you are having it here. So this is time scale, the variation of the displacement of particle P, which is projection of Q on this as function of time. And this, what is that we were able to define? We were able to define 2 things. One is time period of oscillation, Tp, time period, and another one is omega n, circular frequency, and the relationship between them. So do you get any doubt in this? So this is what we were doing in the last class. And you also have studied the statement that there can be 3 vectors now. That's what the 3 equations that we have written. What are those? The position at any point of time, and its velocity and the acceleration. So how these vectors are appearing if the simple harmonic motion is there would help us to understand the phase angle better. So for that, let's look at this diagram here. So in this diagram, you see that this is what the case 3. You see, it is at position some arbitrary distance x. You have this. So at that time, I have my vector x is given by OP vector. So here x vector is OP vector, and that is what is varying. So now you see here, since this Q point, OQ is what is now forming this auxiliary circle, and OQ magnitude is radius of the circle corresponding to maximum amplitude xm. So OQ here, its modulus is xm, maximum amplitude. So if this is maximum amplitude, then and where is this OQ is placed now? It is placed at a distance 5 plus omega nt. So look at now, this OQ naught at t is equal to 0. This is, so we have also looked at the compact form, and that is what is going to be useful now in this. And here OP will be what? OQ. OQ sine omega nt plus phi. So look at this, very interesting. See, this angle here is what is omega nt plus phi. So when t is equal to 0, what is that angle? OQ sine phi. So OQ sine phi would be here. That is what is Q naught referred to. At any time t, I would have my expression OQ sine omega nt plus phi. That's what is given by that. So what is that increment in angular displacement is omega nt from this phi. So at t is equal to 0, this is that initial position, and then in due course of angular displacement omega nt, you have at any time t this OP vector giving you the x vector, which is simple harmonic motion vector, and this Q is a point who has got its uniform speed, velocity, and it circles, so it's always tangential. See this direction. So when you put this direction to the vertical is same as this angle omega nt plus phi. That is also going to be omega nt plus phi. So this helps us to write this further. So first one is what? It is x. So x is going to be xm. OQ is xm sine omega nt plus phi, and x dot is xm omega n cos omega nt plus phi, and x double dot is minus xm omega n squared sine omega nt plus phi. So you have this all. So now you see here this vector coefficient here, xm omega m is what is the amplitude of this vector, and that vector is what is the amplitude of this velocity, and this is directed tangentially on the circle. If I project this velocity vector here, I have for the mass the velocity vector is down. So it is from static equilibrium position, it's going to its maximum displacement xm in the way. So this is the direction of velocity. And you see then here what is directed along this OQ radial line is what is your centripetal acceleration we call, or in this case it is acceleration of this simple harmonic motion, that is xm omega n square. This minus sign, that's why it is upward. So this is the convention, down positive, and this minus, so this is upward, and this is projected on this. So the projection of that is what is sine omega nt plus, see opposite to this angle is this, adjacent to this is cos, that is why here it is cos. So it's very clear here, and this is your acceleration vector. So you see that simple harmonic motion, how do you define? It is always proportional, the acceleration is proportional to the displacement, from its static equilibrium position, and acceleration is always directed towards the mean position. That's why this is directed towards the mean position. So this velocity is going to be 0 here when it is at this extreme position. Why it's so? Because when Q comes and takes this position, it is going to be horizontal here. So vertical component of velocity is 0. So you have your mass here 0, its point of reversal, and then it executes the motion up and down. So this is how nicely one can understand and keep this in mind, this picture. All right. So if you have understood this, so here this velocity Vm given here is, what is this? This is xm omega n, and acceleration is given by xm omega n square, the magnitude, or if I have to, this is in this direction and this is xm now in some arbitrary direction. Sorry, not in this direction. Vm is in this direction, downward direction. This is upward direction, right? So any doubt at this point of time? Anybody? Any doubt? If you do not have any doubt, let's just go to next slide, wherein we are going to revisit again this how this is represented. Yeah.
So can you show that once more, sir?
Which one? The previous diagram. Yeah.
Yes, sir.
Yeah. Any doubt?
Yes, sir. Thank you.
So how do you define a simple harmonic motion? It is the projection of a particle which is executing an uniform motion on a circular path and its projection on its diameter. So if Q is the particle, if you assume, so if it is projected on its diameter, then it is P. So the motion of P is what is now simple harmonic motion, which is projected onto this. And this Vm is going to be constant. That is why you have this natural frequency constant and xm radius is constant. And this axillary circle is helpful for us to understand simple harmonic motion. Right? And you see the direction of acceleration vector is always towards mean position. And velocity is in this direction. So it would be 0 when it reaches to its xm velocity. And the similar way, when it comes to this mean position back, velocity would be maximum and that would be directed in upward direction. So when it's reversing, the velocity direction would change and the acceleration direction would change the other way. Right?
Yes, sir. So, sir, this is taken with 3 vectors, right?
This is taken with?
3 vectors, right?
Yeah, this is taken with 3 vectors because of representing simple harmonic motion, not only by physical observation of its displacement, also look at how fast that motion takes place and what rate that the speed changes. That's what is acceleration. All these 3 vectors are representing its motion parameter. So you have studied in your dynamics of rigid bodies. You are always concerned with what? Finding out displacement, velocity, acceleration in kinematics of particles or rigid bodies, right? You have studied. So here, this is particle kinetics. In particle kinetics, and the kinematic parameters of the simple harmonic motions are given by its displacement, velocity, and acceleration. And these vectors are interestingly having constant some phase angle between them. Let's look at how these vectors are varying. Right, that is what I would like to explain you, and then we will go ahead of looking at how can we represent in the form of complex in complex plane. How can you represent this? So that's my idea of this class. So let's look at now how these 3 vectors can be looked at now. So your displacement vector and your velocity vector and acceleration vector would have what difference in phase angle is what, let me explain and continue, right? Is that fine? So that I will do when I represent this all, you understand that, and you will see. If you look at here, I can rewrite this in this form. So this cos omega n t plus this can be written as what? Plus pi by 2 in terms of sine if I write. Then you see that always velocity, this vector leads pi by 2 angle than this displacement vector, and acceleration leads pi by 2 radians the velocity vector, or phi radians to the vector. That is why you have velocity vector and acceleration vector. So, this is acceleration vector and displacement vector. Displacement vector is this, and acceleration vector is this. So they are 1 pi degree different. So as this comes here, already acceleration here. So acceleration leads displacement vector by phi vector. That's what you have to understand. I will draw the vector diagram clearly before end of this lecture. But now if you have understood this, let's proceed further to understand its advantage of representing in a complex plane, right? So why it's so is, first let us understand, if you have to represent this in a vectorial manner, look at this, maybe I would take the orientation of the vector in the other way now. We can look at that anyway. So this is the circle. I take now here this point on this and a vector representing that, and this vector length say A, and this is now rotating counterclockwise direction with the angular velocity omega. This vector is rotating. The projection of this vector onto horizontal and vertical is what is going to represent its harmonic motion. So I can project it like this as well as like this. So if I project it like this, and if I look at the variation of displacement as a function of the angular displacement, how does it come? Let me draw the diagram and then proceed to the class. So this is what is the vectorial representation. So we require two components to completely understand. So that can be eliminated if you have a complex plane. That's why I just want to explain you this first and make your understanding clear, and then we will go ahead. So now look at here now, what is this is it's y. This is y, variation in vertical direction. And what is this is variation in x direction. So this is the variation in x direction. So let me call this is variation in x direction. This is variation in y direction. So what is y in terms of a? So if this is omega and this angle here, I call this angle theta, and the theta angle is given by omega times t at time t. Correct? The angular displacement of this vector A of magnitude A is given by angular position t theta. So if that is so, what is my y? A sine theta. What is my x? A cos theta. So this A sine theta, A cos theta can represent your simple harmonic motion. Both are required to represent your simple harmonic motion. So let us look at now this A sine theta. So when t is equal to 0, what is this OA vector? It's horizontal. So your motion would start like this. So if this is my y-axis and this is angle theta, I take this as angle theta, and my motion would be from here, it will go and it will execute something like this, right? It will execute something like this. This is theta, this angle is 0, this angle is pi by 2, this is pi, and this is 3 pi by 2, and this is 2 pi. So from 0 to 2 pi, it's what is? It's 2 pi radians displacement, and that's what is equal to omega t for one cycle, and then t is equal to 2 pi by omega. We define like that. In the similar way, you look at this x component variation here like this. So let me extend this line. That's this axis, and then our mean position. Now, how does it going to vary? So let's take now this is my x-axis. The variation from here, it goes to this and then comes back, and then this axis here is my theta axis, vertically. So it is not x and y, x and theta, and here y and theta. Like that you are supposed to look at it. So when t is equal to 0, what was my x? It is at its maximum position. So it is somewhere here. So from there, it executes its motion. And goes like this. So in this, it is now the angle 0, and this angle is pi by, this angle is pi, and this angle is now 2 pi. Right? So this is pi by 2, this is 3 pi, by 2. So like this, you require both components to represent this harmonic motion vectorially if you have to represent. So instead of having this as a vectorial representation, if I have this as a complex number representation, that has got many advantages. I'm going to explain you now that. Right? So what does that explain representation here? Initially, this is vectorial representation. So I have here my x vector, capital X vector, as this a along x-axis. This is I unit vector. This is j unit vector. Right? This is with the j unit vector. This is my y-axis and this is my theta axis. So this axis now can be written as xi plus yj. So what is x here? X is a cos theta I plus a sin theta j. So this is my x vector. So representing this is not so convenient. Cos theta, if I write omega t I plus a sin omega t j. So instead of representing it like this, I'm going to represent it in a complex plane. So that's become very, very convenient. So complex plane is what, instead of calling it as an x-axis and y-axis, I'll call that as a real axis and an imaginary axis. So this is going to be my real axis and this is going to be my imaginary axis. So I have my vector here. Let's call this vector as vector of length A, magnitude A, and I will have this projector on this would give me my real part A, and projector on this would give me my real part, imaginary part B. So this axis is represented by a complex number I. This axis, this is not unit vector, this is complex number I, right? This is complex number I. So Bi, I will say. Here it is real part. So how do I represent my vector now? Is this way. So x vector is going to be A plus IB. A plus IB. Where here I is what is your complex number. So you define that as under root of minus 1. So you know what is going to be I square minus 1. What is going to be I cube minus I. What is going to be I power 4, that's I square into I square I can write, so it's going to be plus 1. So this is how you define your complex number. So I is a complex number defined by under root of minus 1. So if that you understand, if this is my vector x like this, I can represent this vector x as A amplitude times e raised to I theta, e raised to I theta, e raised to I theta. I call this A as absolute value of vector x, absolute value of vector x, and I call this angle theta as the argument. You could have studied this all in your mathematics. So if that is so, I can write this A amplitude by this expression. So A squared plus B squared, and I can write this angle theta by tan inverse of B by A. So this is for one vector. So if I have two vectors and I have to look at them, right? If I have two vectors and if I have to look at them, so vector x1 and x2, how are we going to look at their resultant motion? Is what I will be explaining you now. So you can also prove this all. This form to this form can be proved easily from trigonometric relation. Due to time constraint, I am not going to do. Otherwise, I leave it to you to look at it, right? So I'll just give you an idea. You can do that. So what is cos theta? It can be expanded as in series theta square by 2 factorial plus theta power 4 by 4 factorial So this is plus here, plus and so on. And sine theta can be written as theta minus theta cube by 3 factorial minus theta power 5 by 5 factorial, and so on. So this is what is equal to e raised to, sorry, this we have, this is equation, say 4, and this is equation 5. I can make now this cos theta plus I sin theta. So I'm going to add this. So in that, if I add here, it is going to be multiplied by I every term, and here it is not. So I will have now 1, here it is plus I theta, and here it is theta square. So what I will do, I theta square I will do, I squared is 1, so that is not changing, 2 factorial, and then plus I theta cube. So I cube is minus I. So when I multiply I by sin I, that comes here, so that doesn't change.
Sir, we are multiplying I only for sine, no?
Yeah, that's what is written here. Look at it. Cos theta plus I sin theta. When
Yes,
I
sir.
multiply, so I multiply this series by I. So when I add
Yes.
here, why I put I theta square? Because I squared is 1. So that doesn't change.
Okay.
Right? So this would continue I theta power 4 by 4 factorial and so on like that. And that's what is going to be equal to e raised to I theta. So I can represent this series as e raised to I theta. So I can also write now for cos theta minus I sin theta. So if I put minus here, it is going to be 1 minus I theta plus I theta square by 2 factorial minus I theta cube by 3 factorial plus, so the alternative signs comes by 4 factorial and so on, and that's going to be e raised to minus I theta. So if you have understood this, I can write now my vector x as a into cos theta plus I sin theta. That's going to be a into this would be I can write either this, so I have to multiply with this, so e raised to I theta. So I can have this instead of writing this as my solution, I can also write this as my solution, which should accommodate both the components together. That's an advantage of this. And you also know some of the operations of this complex algebra. So you know how to add two complex numbers, how to find the difference between two complex number, product of two complex number, division of two complex number. So I leave it to you to go through that all. So all we do is all because of what to understand now, addition of two rotating vectors, right? And that forms a simple harmonic motion. So we have understood a rotating vector having its velocity, angular velocity constant, is what is going to give a simple harmonic motion when you project its end on its diameter. That's what we have seen. So if I have two vectors with the same frequency rotating, but they are of different amplitudes, how do I find the resultant? That's what you have to understand now. So let's do now like this. So I have it now. My real axis, my imaginary axis. This is real and this is the imaginary axis. And I have a vector now represented on this complex plane. This is called a complex plane. You are knowing it. So this is a x1 vector. And then I have another vector. This is x2 vector. So how can I represent x1 vector and x2 vector? How can I represent my x1 vector and x2 vector? In this way. X1 vector is a1 or this a1 e raised to I omega t. So theta I am replacing it by I omega t. So x2 vector I can rewrite as a2 e raised to I omega t plus phi. So when I write omega t plus phi, what is this angle? It leads by phi angle. So this angle is phi. So x2 vector is this, and its amplitude is a2, its amplitude is a1. So the length of this vector is a1, a2. So if this is so, how do I find my resultant? So that's where your parallelogram law you have studied, similar way. So complete this parallelogram, drawing this and this parallel lines. And what is that you have here? That vector is what is your resultant vector. What is your resultant vector? So let's call that is vector x, resultant. So vector x is x1 plus x2. So how do I get now the magnitude of this x and its direction and so on? So this direction to x1 is alpha. Direction to x1 is alpha. So now what is the direction of x1? x1 at this time given is at a distance at an angle theta, and that angle theta is this, and that's equal to omega t. And then omega t plus phi is what is this position. So that is how we have taken these two vectors. So now this addition of these two vectors is very simple because of this graphical representation of vector by their lengths and then constituting a parallelogram law for two vectors, addition of two vectors, that helps us. So I'll extend this line, I'll project this on this. Why do I do that so is because this forms a right angle here, and this vector is of same length of a2, and this angle here is same angle of phi. So I have this vector from here to here is now this length is going to be a cos phi, and this length is going to be a sin phi. So now it's simple. From that trigonometry of triangle OPQ, so from triangle OPQ, I would be able to write my amplitude of this. So that's going to be my answer, A e raised to I omega t. I omega t. That angular velocity is not going to change because this angular velocities, both the vectors are same. So I would say here this is not omega t, this is omega t plus alpha, right? Omega t plus alpha. Omega t plus alpha, because you see resultant is from here alpha angle, so this is omega t plus alpha is what is my resultant. So in this I know omega t, that's first vector angular displacement. I know omega t plus phi, that's second vector angular displacement. Both the vectors rotating with the same velocity, circular velocity omega. I have to find replace this 2 by another vector, that's what is this x vector. So this a would be given by now under root of, because of this right angle triangle, I have here this amplitude, the length is drawn with an amplitude, so a1 plus a2, this is a2 and this is also a2, so a2 cos theta square plus a2 sin theta, sorry, sin phi square. So that's going to be my a, and alpha here would be tan inverse of opposite side is a2 sin phi by adjacent side is a1 plus a2 cos phi. See how nicely your parallelogram law helps us here. So if I have this, then I would have my vector x, which is x1 plus x2, and that's going to be real part of x. It's going to be a cos omega t plus alpha. What is the real part of it? The real part of it is when I project it, I'll get it. So you can see here in this way. So if I project this q onto horizontal axis, so what is that I have is real part, this length. So that is small a. And if I project this onto this imaginary axis, what is that I have is B. So this X is what is now A plus IB, if we call. So A is what is real part of this vector and B is what is imaginary part of this vector. So real part of this vector would be A is amplitude you have found, and that is inclined now how much from horizontal? This is that inclination, that is omega t plus alpha. That's why you have it here, and cos of omega t plus alpha. So this is cos of omega t plus alpha. And I can also write in this way, imaginary part of x bar. So that's going to be A sine omega t plus alpha. So if I have to write this as my resultant vector, and I need to find out amplitude and alpha here. So now here, what does this angle phi? Phi angle is phase angle between the two rotating vectors. So if I know phase angle between two rotating vectors and the respective amplitude, if they happens to go with the same velocity, angular velocity, this is the answer. So since here the omega of both the motion, both the vectors are same, since omega is same for both vectors added, they are called synchronous vectors. Synchronous vector. So what do you mean by synchronous vector? Synchronous vector essentially would have same circular frequency and can have different amplitudes, and you can add the two synchronous vectors, find its resultant, the method or the procedure that I have explained now. Right, is that clear? Any doubt? If you do not have any doubt, I will stop at this point of time. And this is again an important understanding when you say that you know fundamentals of mechanical vibration, and they are all looking at rotating vectors. Of course, I have not looked at the vector diagram of your simple harmonic motion. That is the point to start next class and go ahead with adding more and more of this. So whatever that we were doing today and last class, all are confined to free vibration because they are only induced by an initial condition. And also it is very interesting that you have defined time period and natural frequency. They are independent of initial conditions. They are independent of initial condition. They only depend on the mass of the body executing simple harmonic motion, not even the weight, because G is constant. So mass of the body and its elastic property of that is only is depending or dictating the time period or frequency. Initial condition is no matter. So there are three cases of initial condition today we have seen that can be displacing with the initial velocity from mean position, or releasing it from an extreme amplitude position with zero velocity, or at any point of time giving both the displacement and initial velocity and making it to execute the motion. So the motion would be with a similar way, and they will not be, that initial condition will not influence your omega and your time period. That's what is the conclusion, and today's class I stop. Right? If you have any doubt, please ask. Otherwise, I will end the lecture. I'll stop recording.
Yes, sir.